Let us solve another question. We have to find out the remainder of the number 37 raised to 49 when divided by number 7. So there are 4 options. First option is 3, second is 1, third is 2 and fourth is 6. Now what is the meaning of this? It is just when you write this 37 raised to 49 congruent to, you just have to find out this number, say x modulo 7. So the natural question arises, how to find this x, right? So there is a famous theorem called Euler's theorem which says that a raised to phi of n is congruent to 1 mod n, where this a is an integer such that the GCD of a and n is 1. Now you just take that a to be 37 because we want here 37. So take a to be 37 raised to and this n to be 7. So 1 mod 7. And what is phi of n? Phi of n is just phi of 7. Now just note that this 7 is a prime and we know that phi of p, where p is a prime, it is just equal to p minus 1. So phi of 7 will be 7 minus 1, which is 6. And just note that the GCD of 37 and 7 is 1. So this is we can apply Euler's theorem here. Now just note that we want here 49, right? So in order to get 49 or a number closest to 49, we just have to take this power to be 8. Then we will get this as 37 raised to 6 raised to 8, same as 1 raised to 8 modulo 7, right? Now this 37 raised to 6 into this 8 will be just 37 raised to 8 into 6 is 48, which is congruent to 1 raised to 8 is 1 modulo 7. Now we are near to this 49, right? This is 48 and this is 49. So you just multiply it by 37. So we will get this 37 into 37 raised to 48 is congruent to, now we are multiplying by 37, right? So right here 37 into 1 is just 37 modulo 7. So this will be just 37 raised to, here it is 1, here it is 48, so just add them, it is 49 congruent to 37 mod 7, right? But just note that these options are 3, 1, 2 and 6. So we need to just write 37 modulo 7. So 37 is just congruent to 2 modulo 7 because just note that 7 divides 37 minus 2, right? Because 37 minus 2 is just equal to 35 and 7 divides 35. So you can write this as 37 raised to 49 is congruent to 2 modulo 7. That means this, the value of x here, it is just 2. That means the remainder is 2. So the third option is the correct option. Let us see another question. We have given a group Z36 and we have to find out the number of left cosets of the subgroup generated by 6 of Z36. So let us just denote this group generated by 6 by the letter H. So we have to find out the number of left cosets of H in Z36. That means the number of left cosets of H in the group Z36, which is just equal to the index of the subgroup H in the group Z36. And we know that this is just same as you just write down the order of Z36 and divide it by order of the subgroup H. So what is the order of this subgroup H? It is, now this H is equal to a subgroup generated by 6. So these are just multiples of 6. So start with 0, because 0 into 6 is 0. So 0, then 6, 6 into 1, 6 into 2 is 12, 6 into 3 is 18, 6 into 4 is 24, 6 into 5 is 30, then 6 into 6 is 36, and so on, right? Now you just note that this 36 is same as 0 in Z36, right? Because 6 divides this 36 divides 36. So order of H is just equal to, so this is same as 0, so we should not count it again. So this is 1, 2, 3, 4, 5 and 6. So the number of elements in this subgroup is just 6. That means order of H is 6. So what is the answer? It is just, you write down the order of Z36, which is just 36, divide by order of H, which is 6. So the answer is 6. So the second option is the correct option. Let us solve another question. We have given a group G and H be a finite subgroup of the group G, and let us fix an element small g in the group G, and if this GHG inverse is equal to the set G small h G inverse, where this H is an element of H, then there are 4 options. The order of GHG inverse is same as order of H. Second option says that order of GHG inverse is less than order of H. Third option is order of GHG inverse is greater than order of H. And the last option is the order of GHG inverse is equal to 1. Now we know that if H is a subgroup of G, then the order of GHG inverse is same as the order of H, because we can just write the bijection between these two sets. So let us take f, a function from H to GHG inverse. Now, and this G is a fixed element of the group G. Now you just take a small h and map this h to GHG inverse, right? So now this h is an element of this capital H, so GHG inverse is an element of G capital H G inverse. So we can define the map like this. Now we just show that this F is a bijection between these two sets. So what do we have to show? We just have to show that this F is 1, 1 or injective and onto, right? So that this F will be a bijection between H and GHG inverse. So let us first prove that it is 1, 1. That means F of H1 is equal to F of H2 must give us H1 is equal to H2. So what is F of H1? It is just GH1 G inverse, and F of H2 is GH2 G inverse by the definition of F. Now we know that these elements are in group, so we can use the cancellation property, and hence this G will get cancelled and G inverse will get cancelled with this, and we will get h1 is equal to h2. Hence f of h1 is equal to f of h2 gives us h1 is equal to h2. That means this f is 1, 1. So this is done. Now in order to show that this is onto, you take any element from this set GH G inverse. So the element is just G H G inverse belongs to GH G inverse. Now note that this H belongs to the capital H. So you here this f of h, you just take this h, and f of h is equal to GH G inverse by the definition of f. That means for every element in this set GH G inverse, we have a pre-image, namely this h. Under this f, this element h is mapped to GH G inverse, right? That means this f is onto. So this is also done. That means this f is a bijection between these two sets. That means the number of elements in these two sets are same or equal. So the cardinality of H is same as the cardinality of GH G inverse. So always remember that these two sets have the same number of elements. So first option is the correct option.